Okay, I will start the session. Meanwhile, students can join. I think my audio is audible. If it is, if you are facing any issue, please let me know. Okay, I'll share the presentation. Uh, I hope my presentation is visible. I'll wait for students. Okay, then I'll proceed further. Good evening, all. My name is Shriyari. I am the teaching assistant for the course Advances in Welding and Joining Technologies. This is an NPTEL problem solving for this course, and the course tutor is for Professor Swarupa. And today is the fifth. Okay, I think I didn't unmute it. Okay, sorry. I think now my audio is visible, right? Yeah. Okay. I think it is audible and I am visible. Okay, then I'll start the session. Uh, Good evening, all. My name is Srihari. I am the TA for the NPTEL problem solving for the course Advances in Welding and Joining Technologies. And the course tutor is Professor Swarupa, and I am the teaching assistant. My name is Srihari C. And this is the fifth live session for the fourth assignment. As now we are like as earlier we are discussing of discussing the last year's assignment and this year's previous assignment in the current week. So we are discussing about the fourth assignment. Okay, we'll proceed further. Of the first 10 questions will be of last year's and next 10 questions will be of this year's. In an arc welding process, which of the following parameters has most influence on the material's flow magnitude and direction within a small weld tool? Basically, in arc welding means electromagnetic force will be there, buoyancy force will be there, monogamy means surface tension, this thing also will be there, arc pressure also will be there. But here they have mentioned which of the following parameters has most influence, because main thing is like surface tension force or monogamy stress is like it is the attaching force. So we need to overcome for the droplet to detach. So based on this magnitude only, the arc stress or buoyancy force or electromagnetic force will be dependent. So answer one for first question, B will be the main B will be the answer. I think you guys understood, and also I think in second or third session I have explained about the why how arc pressure is created here, something like this. If you have any doubt, I can show those diagrams at last. Uh, for first question, answer B, Maragani stress, because the surface tension is the attaching force. So to overcome that, we you corresponding process parameters like current, voltage, hence the generated electromagnetic force or and also the buoyancy force and all, along with the arc pressure, droplet will get detached. So Moragani stress is the main answer. This actually in the double electric resource model, which of the following equation represents the volumetric heat source distribution for rare ellipsoid. Here they have mentioned like rare ellipsoid. In the sense, if it is only ellipsoidal heat source means we'll have entire ellipse. But in double ellipsoid, what happens is like we'll cut the two ellipse and we'll merge it, right? So front part of the ellipsoid will be different, and rear part of the ellipsoid will be different. From the two different ellipsoids, we'll cut them and we'll merge it. So now they have asked is like uh, in the double ellipsoid heat source, which of the following equation represents a volumetric heat source for a rare ellipsoid? So, so first of all, we'll check the options. Yeah, F or rare is there, and also AR and AR is there. So in the double ellipsoid equation, only these terms will change. Rest in for front and back. That AR and AR means geometric parameters in rear direction. AF means geometric parameter in front direction, and FF means fraction of heat source deposited in rear and front thing. FF means in front thing. FF means so suppose for a given Q, how much factor we are giving it for front portion of the ellipsoid source and how much we are giving to the rear part of the ellipsoid. So that is determined by FF and FR. So basically, in other options, I think 2A is the answer. Uh, because they asked about yeah, yeah, A is the answer because they asked FR and AR, and also one second. Yeah, here pi root pi is there. In the other C and D, the pi root root pi is there. Either pi is there. So this formula is entirely wrong. So for a rare ellipsoid, for rare ellipsoid we'll use this. For front ellipsoid we'll use this. So, a question asked is like rare ellipsoid. So 2A is the answer. That's what is explained. Uh, like this these three terms will only change because those only changing in the those ellipsoids. Other than that, the geometric parameter in width, the geometric parameter in width or a depth of the ellipse will remain same for both ellipsoid. So B and C will remain same. Only the A means major axis in front and rear ellipsoid will change. So based on that, AR will change, and also as I said, FR will change. So so that is the thing. So for the second option, A is the answer. This is actually straightforward, which is explained by sir in the class. Which of the following if someone have any doubts, you can post it. Which of the following equation represents the temperature distribution T r comma T means it with respect to r and time. R is a radius for an instantaneous point heat source means Rosenthal's equation by considering the infinite body and zero initial temperature, where R is like this thing. This is clearly explained by sir, and it should be 3 by 2 because it's the square root of x square plus y square plus z square, and also alpha term is not here. So 3A is the answer. That's what explained below. Like temperature distribution for instantaneous by considering the infinite is given by this equation. So basically, you need to be familiar with the given equation. And also if you want to learn how these equations are arrived and all, you need to study the papers. Basically, this is developed by double ellipsoid heat source is developed by Goldak paper. Goldak thing. It is from the paper around like 1983. He has developed at that time. Even now also we are using for numerical simulations. Even for analytical solutions also we are using these equations. That and this and the paper which he has given these given these equations and all. It is the most cited one of the most cited one in the welding community especially. that much powerful is that paper. If you guys want to understand clearly, uh, you can go through that Goldak paper. If you want a title, right now I don't have the title. I can share it later if you want. Okay. Similarly, this is this thing. The equation is directly given. So the question is like an arc welding process is carried out at effective heat input. So Q is 1800 watt and welding speed 4 mm per second. Based on Rosenthal's 3D moving equation. So just now I said you guys need to be familiar with the equations. Basically Rosenthal's standard equation and also Rosenthal's equations and also ellipsoidal equation. If you know the ellipsoidal equation, you can directly uh, get to know about the double ellipsoid just by changing the terms and all. So you guys need to know the equations, and if you want to further study that, as I said, you need to study those research papers. An arc welding process is carried out at effective heat input of 1800 watt and a welding speed. So Q is 1800 and the welding speed is 4 mm per second. Based on Rosenthal's 3D equation for moving heat source, calculate the temperature generated. Okay, he is asking temperature generated during the welding process at location x is equals to 10 mm, y is equals to 10 mm, z is equals to 2 mm from the origin with the following parameters. So ambient thermal conductivity, density, and specific heat. So the formula is shown in the class, and I also derived. Means derived in the sense, sir has shown how it can be derived. First of all, this is the formula. T is equals to T naught plus Q by 2 pi K R x e power minus V R minus x divided by 2 alpha. This V is velocity, R means radius in the sense this thing, and x means how much away we are, means what is the point of interest, and then this is alpha means thermal diffusivity. So first of all we need to find the alpha. So for alpha, that the formula is the K by rho Cp. That is the known formula. Even you guys would have studied in heat transfer on those things also. So thermal conductivity, first of all, whenever we solve the problem, you need to be sure about the whether we are using SI units or same units. So first of all, K, what is the K? 30 watt per meter Kelvin. So this is the standard SI unit. So density kg per meter cube 7000. The is also standard unit, and specific heat is also in standard unit. So we can directly substitute, and we'll get the alpha once you solve this thing. After that, we need to find the R, right? Basically, R is equals to square root of x square plus y square plus z square. That is also known. But here they have mentioned 10 mm in terms of mm. So we need to convert into SI units. For distance and all, SI unit is a meter. So we need to convert it to meters. So once you get this, it will be in mm. Then you need to multiply it 10 power minus 3 to get in mm. So this is the value. Once that is done, we know that Rosenthal's equation is given by this. Just after that, there is just substitution. One more point. Yeah, here T naught. Here he has given as 25 degrees Celsius. Since SI unit for temperature is Kelvin, we need to add 273 Kelvin. 273 plus 25, 298. That is the point here. So Q is also in watts. So divided by 2 pi kr. Everything is known, and also e power minus. Since velocity, I think, where is the velocity? Yeah, velocity is 4 mm per second. Here we have mentioned like 4 into 10 power minus 3 to convert into SI unit. The main thing is like you need to be familiar with the formulas, and also once you are familiar with the formulas, you need to substitute in SI. You need to substitute in. You need to substitute in SI units so that you get the solution. So R, we calculated the R as 0.0143. So we are substituting that, and X is given as 10 mm. So we need to convert it to SI units. So we need to substitute here, and finally we need to substitute what is the thermal diffusivity alpha, which we got from this K by rho Cp. Once we solve this Rosenthal's 3D equation, we'll go to the temperature at the particular point x is equals to 10 mm as 432 Kelvin. Uh, so the answer is C. I know I'm not writing everything because I'm just explaining in words. Uh, Main thing is like once you know the formula, you need to substitute it. You need to substitute the SI units. That's it. Uh, yeah, then your life will be simpler. So for fourth one, C is the answer. Okay, I think I'll proceed for further. This is actually, I think, melting efficiency. This is also most almost this is also straightforward solution. Like during the arc welding process, the welding current, voltage, and thermal efficiency of the weld is so they have first they have given the parameters what is used in the given experiment. If the heat required to melt the metal up to melting point, uh, including latent of fusion is 1200, calculate the melting efficiency. So uh, here like okay, they have asked us to calculate the melting efficiency. Basically melting efficiency formula is like q1 by q1 in the sense heat required to melt the weld metal up to melting point, and also up to melting point, and also there is a latent heat of conversion, right, from solid to liquid. So that part, that is q1. So he has directly given q1, and we need to calculate q is nothing but the what is the amount of heat input, I can say. That is heat input in watts. So that is directly given by voltage into current and also into efficiency. He has mentioned 0.75 as efficiency, and this amperes is the SI unit, voltage is also SI unit. Again, I am stressing, whenever you solve a problem, if you are convenient with solving with any units, that is fine, but it's better to solve it in SI units. Uh, so, uh, so these are in SI units. So we'll directly get it in. Then no need to think about which it will come, like joules per second or kilojoules per second, something like that. So directly, since it is in SI unit, we'll directly get it in watts. Once we get it in watts, we need to substitute here. Once you solve, we'll get it as 35.55%. So approximately the fifth 5C is the answer. Okay, I'll go a little bit faster since time is already okay 6:20. An arc welding process is An arc welding process is carried out at a welding current of 200 amps and arc voltage 13 volts. Assume that ambient temperature is 25 degrees Celsius. The thermal conductivity is 25 watt per meter Kelvin, and heat source is moving along x direction with velocity of 5 mm per second. So first of all, whatever is given, you need to convert it to SI units. That is fine. Then based on the calculate the temperature gradient. I think you guys should remember this Rosenthal's temperature gradient, or else you need to know the base equation. Then from there, how to derive that. At least you need to know that. Uh, so first of all, this is the thermal temperature gradient, dou T by dou X, with respect to distance, right? For a given time. So this is the formula. So for that, again, we need to calculate Q. Q is equals to VI. So this is like 2600 we'll get, and we'll substitute the corresponding thing. One more thing, like here again, you can ask why you are not substituting it in SI units, like 625. Because since it is difference, if you want, you can convert in SI units, and you can again take, you will get the same difference because it is difference. That plus factor will get plus 273 here, and plus 273 will get cancelled. So ultimately, if it is Celsius, directly you can directly substitute Celsius since it is in difference. So once you substitute, we get it as minus 20. So 6B is the answer. So these things and all, like sometimes we need to convert it to SI units, sometimes you no need to convert it to SI units. So if you are familiar with solving problems frequently, these when to change, when not to change, you will easily get to know. So which will be useful for gates or solving also. Like in gate also, you need to solve as soon as possible, like a time limit and all. So that's why. Okay, next question. Uh, See, in our What is the question? In a gas metal arc welding, the wire. Sorry, this is the wire. I think it's visible. Okay, anyhow, this is the pen I am keeping holding. 1 mm diameter. So it is being fed the diameter with the. I think you need to picture is the schematic, right? It is being fed with a constant velocity. That velocity is wire feed speed. How much speed the wire is fed. Uh, that is also process parameter in GMAW. The density, specific heat, and melting temperature of the mild steel wire is given here. They're fine. They have given this respectively, and ambient temperature 25 degrees Celsius. And they have also mentioned like neglect the latent heat of fusion. Fine. Then, if the total amount of heat required to melt the weld metal is 1080 watt, calculate the wire feed speed. Uh, so they asked us to calculate the wire feed speed. First of all, we need to know that for any material, suppose this is a wire, if it is in a room temperature, then to melt this, we need to raise this wire from room temperature to melting point temperature, right? Along with that, from solid to liquid, we need to use latent heat. Here they asked us to neglect the latent heat. So I am directly so what is the mass of the material, and so to calculate that we have a standard formula like heat required. Q is equals to mcp delta T. That is there, right? And here they ask us to neglect the latent heat. So Q actually to melt the material, Q is equals to mc plus delta T plus latent heat. So now they asked us to neglect latent heat. So Q is equals to mcp delta T. But here wire is fed. So uh, m dot delta T, m dot cp delta T. This m dot in the sense area of the cross section into like volume, mass is equal, density is equal to mass by volume. So volume into density. So that volume into density, right? Volume is this is the cross sectional area, and density is given, and wire feed speed. Since it is a feeding, we are substituting in V. Uh, so VA rho AV CP TM minus TA. So A means this is a circular rod, right? So this cross-sectional area, how much we fed? This cross-sectional area is this is if it is having a diameter of D, then the cross-sectional area is pi d square by 4. And how much speed it is fed? Uh, mm, so we can calculate the volume, how much it is deposited. So A into V, the volume is there, then density, then other terms. So uh, so while substituting pi d square, since it is 1 mm, 1 mm, since it is in mm, we are converting it to 10 power minus 6. Since it is d square, we are converting it to 10 power minus 6. Then density is the SI units, and also Cp is given as 1000 kilojoule per kg Kelvin. And then again, this is difference. We can directly take 1435 minus 25, so we'll get this term. So ultimately, we need to calculate V. Since Q is given as 1080 watts, so we can directly substitute 1080 watts. So after substitution and solving, we'll get it in 0.125. Let me check the time. Okay, fine. So 7D is the answer. I think if you guys know the formula, you can directly answer this also. So few formulas are there that you need to be familiar. Uh, these formulas are very important for numerical simulation also, analytical modeling also. Understanding the welding mathematically. Uh, First of all, you need to understand how those equations are derived, or how uh, point source to volumetric is how it is emerged and all. For that, you need to read some research papers related to that. Okay. Which of the following equation represents the cooling rate derived from presence of 3D equation on semi-infinite body? These terms are like heat input, K is thermal conductivity, as we know, and V is the velocity of the heat source in its direction, and T naught are the temperature generated and ambient temperature. Fine. So we'll get the equation as 8B. So this is the equation, because what they have asked is they have asked what is the temperature generated or temperature gradient, right? Now, uh, oh sorry, it's not temperature gradient. They have asked cooling rate. Okay, fine. Cooling rate they have asked. Uh, so for cooling rate means change in temperature with respect to time. So dou T by dou T is this is given by this formula, and we I think last few problems also we saw the temperature gradient as this formula. Uh, dou x by dou T means uh, change in uh, change in the dimension x with respect to time means that is velocity, right? If you substitute this in equation 1, we'll get this equation. Uh, so what is the answer? Minus 2 pi v t minus t naught whole square by q. So B is the answer. I think if you read this and if you understand Gaussian, not in this and in your math, intermediate maths also, at least you can tell this answer because basically heat density or any value you can directly, if you know the Gauss, you know that we can represent the welding arc sometimes as Gaussian distribution. So now question is like which of the following statement is correct about the Gaussian distribution of the heat source? So Gaussian distribution of heat source means I don't know my writing skills how it turned out. Okay, actually it should be symmetry. Think that it is symmetry. So at the center it will be maximum. As we go away, it will the value of the like in heat intensity will reduce. So uh, so the solutions are like so heat density is maximum at the outer periphery. No. The heat density is maximum at the center, and as we go away from the center of the arc, so this is the arc, something like this. This is the electrode, and this is the arc. This is the base plate, and on the base plate, how the heat density is distributed, given by this. Uh, so someone has given like I don't know. I think I missed it in some. Okay. Uh, so this is not a thing. Heat density is maximum at the center of the arc. That is true, and heat density is decreasing exponentially because obviously Gaussian is you would have not you would have studied in probability also, right? Like a normal distribution means that it's exponentially decaying and all. So heat density is decreasing exponentially in the radial direction from center. This is also so it's not linearly decreasing. So 2 and 3 is the answer. So here 9C is the answer. Let me show the explanation. So in general, we can represent the Gaussian like this, and C is the, as sir said in uh, distribution coefficient, like how much, whether it is stiff or whether it is elongated, something like that. Based on this, uh, C only it will change. If you guys are familiar with MATLAB plotting and all, you can check with this. You can check it in MATLAB by changing this coefficient C to see whether how the Gaussian is changing. And this is R. So at particular radius R. Uh, so from the above equation, we can so if we substitute values, you will directly get the no, and it's exponentially decaying. So 9C is the answer. Let I just give the answer to this question, and as sir mentioned in the classes also, so the slides is there. So, but at last, what is the short pinning or surface hammering or hammering or surface welding will do? How it will reduce the what like how it will reduce the resistance generated in the component and all. I'll explain. So first one, like which of the following technique is technique to minimize the distortion in a large welded components. Uh, so Here, the options given are like short pinning, hammering, surface welding. Basically, these three are used to reduce the residual stresses. Uh, but they are asked like distortion. So, tack weld at multiple joints can be used to reduce this. So, 10D is the answer. I'll come over. I'll explain these three things, or at least I'll give the insights like what's happening with the help of this. How we can able to reduce the residual stresses. I will explain in later stages. At last. So, because of in order to minimize distortion, it is recommended to tack weld. It's already discussed in class. If and also if slides also it will be available. Again, this year also, November this year's assignment is recent assignment. So this question also related to somewhat like this, little modified thing. Which methods are not used to relieve the restrictions from weld parts? Obviously, this is not used to relieve because it is used to reduce the distortion, and other things are used to relieve. Uh, uh, so basically, I will explain this too, but how the selecting the appropriate building sequence also changes the residual sections. If I had shown some figures, then it would have been easier for this to understand. But today I didn't use the. Today I don't have this image for this. Uh, Even in welding also, in additive manufacturing also, the how we are going to deposit, whether I am going to deposit like this, like this, like this, or I am changing the sequence. First I dot deposit here to here, and then I will change it from deposition from here to here, and how residual and distortions are changing. That is also there. So that's where this numerical simulation, the thermomechanical modeling and all helps. So before doing experiment itself, suppose if I want to deposit a 3D component, whether I should go with the given sequence or whether I should change the sequences, means I should change the start and end points, or I should change the completely the, suppose if I am depositing from here to A to B, and then after that if I am depositing from B to A, whether it is changing or not. Suppose if I am depositing a rectangular component, so whether if I continuously depositing from this point only, like suppose this is a point, so I am depositing like this, I am depositing like this. This is a start point and end point. Whether I need to change this point from here or here, so this sequences also matters. So with the help of simulations, thermomechanical modeling, we can directly tell that which is the optimum sequence we can follow so that we can reduce the residual development of the residual stresses. Since if we reduce the residual stresses, obviously we will achieve the components with the better properties, right? Mm. So maybe next if next session, if possible. Okay, I'll try to show the figure of this. Okay, so option 11A is the answer. You guys are following it, right? And hopefully you guys are following. Okay. Uh, which of the following equation represents the volumetric heat source at the center of the ellipsoidal heat source model, where A, B, C represents the semi-axis of the ellipsoidal heat source and Q is the powering. Okay, basically that thing is like uh, suppose if ellipsoidal heat source is given, it is defined from with respect to center. From that center, origin starts. From there, that parameter, that distance will change, right? So at the center, x, y, z will be 0. So suppose if you substitute that x is equal to 0, y is equal to 0, and z is equal to 0 in the equation, you will get the final equation. Actually here they have just asked about the ellipsoidal heat source. Here the equations are like double ellipsoidal heat source. Anyhow, one and the same. The catch here is like you need to substitute x is equal to 0, y is equal to 0, z is equal to 0. So once you substitute x is equal to 0, y is equal to 0, z is equal to 0, basically e power 0, e power minus 0 or 0. Anything to the power 0 is 1. So this whole term won't be there. This will become 1. So okay, you guys understand, I think. Already time is a bit lagging with time today. So these terms will become 1. But here they have given ellipsoid only, not double ellipsoid at this thing, double ellipsoid. So this FR will become F only and AR become A. Because in ellipsoid, all the other dimensions are the same. So 6 root 3 F NQ divided by AB, this ABC pi root pi. In other terms, A square, something. So if you know the formula, you can directly get the. These are like ellipsoid and Rosenthal. If you know, if you remember properly, like it's very important for this computational, computational of welding, like through whether it is analytical modeling or numerical modeling, those things. So 12B is the answer. Again, this question is also based on the equation itself. Mm, so we know that cooling rate delta dot T by dot T is given by this. So thermal gradient means dot T by dot X, right? Dot T by dot X. Okay. And this is the okay, this is the equation. So what is asked like temperature gradient? This temperature gradient dot T by dot X increases with increasing temperature difference. Yeah, obviously it is directly proportional, right? T minus T naught. Yeah, fine. And also you don't see this negative term. This is just a directional thing. So don't see this thing. That only show. So basically, that is magnitude is the important thing. Uh, Vivek has said like A in 13. Yeah, the temperature gradient increases with increasing temperature because it is directly proportional, and also temperature gradient decreases with increasing heat input because it is inversely proportional. So for 13, A is the answer. So a double ellipsoid heat source model is used to simulate the multiple welding process under the following parameters like voltage is equals 26, current and they have given 230 amps, and also half width is 4 mm, depth of the ellipsoid is 12 mm. Okay, they have mentioned everything. Uh, heat input heat input uh, heat input fractions for front and rear is also given. Then so they asked us to calculate the front and rear heat flux ratio. Okay, like QR by QF, right? They have asked QF by QR. Yeah, Vivek, your answer is right only. But for the sake of clarity, I will explain. So they ask us to, yeah, C is the correct answer. But they are, for the sake of clarity, I will explain. Uh, so like this is the rear part, this is the front part, as I explained earlier. So this at the center, I think they have mentioned at the center also. So as I explained, this term will be 1. So only we left with this thing. So what we'll get is like ff f ff divided by af into, I'm sorry for this, af into then ar fr. Then here like zero point 0.4 and 1.6. What is that? Heat input fractions. So for front zero point 0.4 and this is 1.6. This is 1.6. Then this is a 16 and this is for something like yeah, 16 for rear and 4 for this thing. So if you substitute and if you calculate, maybe I would have used wrong this thing. Basically if you substitute and calculate, this turns out to be 1. Which of the following statements is correct? So preheating the base parts minimize the distortion. Yeah, obviously it will minimize the distortion. So this is also this is correct because the thermal gradient will reduce because so all of a sudden if I deposit a component, the temperature will be more here and away from the weld, the temperature will be less. So there will be more temperature thermal gradient because of that thermal contraction and happen those things because of that. Uh, uh, Distortion will be there. Yeah, D is the answer. Yeah, the cooling rate does not affect the. This is obviously wrong. The whole point is like simulations and all. Like one of the main point is like calculating the cooling rate. From that, uh, uh, from the main point of numerical simulations or analytical simulation is like we'll get the temperature distribution. From that, whether we can calculate residual stress or distortion, and also with the help of if we have temperature distribution, we'll get the cooling rate. From that also, we can calculate the microstructure. That is the point, right? So this is not the thing. The cooling rate affects the yeah, it affects the thing. So this 1 and 3 are correct. And Newton reflection is the destructive technique. No, it's like a non-destructive technique. The destructive techniques like contour method or hole drilling method, those things are the destructive techniques for residual measurement. Here the neutron destruction, based on the Bragg's law, it will solve. As we discussed, Sir has also discussed about this, so I don't discuss much about that. Also lagging behind the time. So 15D is the answer for 15D. Okay, in fusion welding process, uh, the cooling rate is given, the solidification rate is given, the temperature gradient is estimated as. Basically, you need to know the relation. Cooling rate is given by G into R. G means thermal gradient, temperature gradient, R means solidification rate or growth rate. Uh, and also in welding metallurgy, sir will I think there will be a discussion about how this G by R and GR influences the microstructure size and also the which microstructure will obtain. I think there will be a discussion about that also. During that assignment, we'll look into that how it influences the microstructure, or what kind of microstructure will achieve based on the values of G by R and G into R, GR. So basically, GR is equal to cooling rate. Uh, so they ask us to calculate temperature gradient, right? So we need to calculate G we need to calculate. Cooling rate is given. So R is so cooling rate is 100 K per second, it's Kelvin per second, and this is mm, 8 mm per second. Uh, so since they have asked for Kelvin per mm, so Kelvin per mm, so 100 divided by 8 will get like 12.5 Kelvin per mm. So 16A is the answer. If you want, guys, actually, because of time constraint only, I'm not explaining the principles of X-ray diffraction and neutron diffraction. Basically, these two are Bragg's law and contour method. How that non-destructive method of contour. So, basically, as sir said, there will be stress relief. Uh, Suppose if there is a component, if I want to check the resources, I will drill in fluid way. If I drill a hole around that, I will keep the strain gauges, and if I drill a hole, because of the hole, stress redistribution and stress relief will happen. Because of that, there will be some kind of strains in the nearby region. So if I place a strain gauge, I will get the strains, right? In the strain gauge. Strain gauge, basically strain gauge is used to represent the how much of stress, how much of strain happened. So you guys would have studied in strength of materials also. So yeah, I'll place a strain gauge because from that strain gauge we'll get the strains and stresses. So basically, with that I can calculate the resolutions and all. So basically, Bragg's law, X-ray diffraction is basically given by Bragg's law, and also Sir has given some formula also, right? Like some 2D lambda sin theta. I don't exactly remember. If you guys want, next class, if I remember and if time permits, I will explain the basic principle of this various measurement technique. Or else, when online also you get many material. If your research interest means if you further study or further work interest in that direction, you can go through that online material also. So basically, 17 like Newton refraction and X-ray diffraction. So where is that 1 and 4? One is 1 and 4 and 4. So see, right? Yeah. Follows the basic principle. Yeah. This is also correct. This is also correct. Basically, generally, what happens is like Q is means like amount of heat input, like whether you can mention it in joule per second or joule per mm. So in this question they have mentioned current and voltage. So and they ask us to calculate joule per mm. So joule per mm in the sense, if you directly calculate VI into efficiency, you'll get it in joule per second watts. So we need to divide it by welding speed to get it in joule per mm. So that is the thing, like 0.85. I'll tell orally, like 0.85 into current 26 into 230 divided by 5. If you substitute, you will get answer as, I don't exactly remember, 780, around 1020 or something, 1018 something. I'll get, you need to multiply this and efficiency divided by welding speed. This is also a bit involved. Basically, we know the concept, means that is also easy only, and also it's already discussed in class. A butt joint, a butt joint is made using an arc welding process at a current of 140 amperes and arc voltage of 20 volts. A mild steel wire of a diameter 1.2. Okay, here they have mentioned diameter as 1.2 mm is fed at a feed rate of. Here you need to be careful, like 138 mm per second. The wire fed is at the amount of wire, the velocity of the wire feed rate is like 138 mm per second. So you need to be careful, and properties like density and also specific heat and melting point of that is given, and also ambient temperature is 25 degrees Celsius. Uh, our main point is like latent heat is not given, and they ask us to neglect the latent heat. Calculate the amount of heat conducted to the surroundings. First of all, Q means amount of heat input, and Q1 means amount of heat required to melt the given material, and Q2 is like amount of heat evaporated, like not evaporated, heat conducted to the surroundings, and also taking some given liquid to separated state in this term, in this context. So basically, this is the thing I have taken from Sir's slide only. So they asked us to neglect latent heat. So we can calculate directly, right? Based on the, I think I have solved this problem also. Let me check. I think I have solved this problem also. Okay, so rho AB and Cp is the specific heat, and the melting temperature is already given. And what is the ambient temperature? It's 25 degrees Celsius. And A is the cross-sectional area. The cross-sectional area, how we can get? Based on the diameter, right? Pi d square by 4. Because the wire diameter is cross-sectional area, how much volume it is getting deposited. So based on the velocity and the cross-sectional area, we can calculate that. I think this is visible. So latent heat is gone. So density is given directly. A means pi by 4 into d square, pi d square by 4, right? D means 1.2 mm, 1.2 divided by 1000, because we need to convert it to SI units, whole square, into velocity is given as 138 divided by 1000 again, because he has given as mm per second. The problem it has given as mm per second, and also this is directly, right. Cp means 1000, it is mentioned specific heat, and delta T means 1435 minus 20. So if I substitute this, I'll get this value in SI units. Once we get this, and also it is asked to calculate Q minus Q1, because uh, like it is the heat liquid overheated and also to conduct it to surroundings, and it is asked to calculate that. Uh, so Q2 is equals to Q minus Q1. So Q, as we know this, efficiency into I into V. So 2520 will get 2520 if you substitute the value of 140 amps and 20 kilovolts, sorry 20 volts, but not kilovolts. And the efficiency as given, some efficiency will be given 0.9 thermal efficiency. So that will be 2.2520 minus 1716.5 something. I will get around 803, 804, something like that, and the nearby answer is 805. So actually, in this conversion, like pi and all, based on the decimal accuracy, the value will change. So, so 19C is the answer. So this is the last question. So in an arc welding process is carried out. An arc welding process is carried out is carried out at a welding current of 120 amps and arc voltage is 15 volts. Assume that ambient temperature is 25 degrees Celsius. The thermal conductivity of the steel is 25 watt per meter Kelvin. Arc transfer efficiency is 0.85, and the heat source is moving along x direction. Uh, Basically, this is like Rosenthal 3D equation. Uh, so, as I said earlier, you need to be familiar with these things. So, what they ask like cooling rate, dou T by dou T. Okay, this is the thing. So kV and all, if you substitute T minus T naught, that is temperature things. If you substitute and if you substitute, I think you'll get the answer as minus 187. So yeah, you'll get it as minus 187. This is basically by substituting it in SI units. That's it. I think this thing I have discussed. Okay, this particular question is like. This what is the surface rolling, short pinning, hammering, and uh, how it will reduce the like elevate the generation of residual stresses, how it reduces the residual stresses in a given component or like something like that. So basically, surface rolling, hammering, short pinning to generate the compressive stresses, and with the help of that, it will remove the tensile residual stresses generated in the component to reduce the residual stresses. Okay, I will explain with a little explanation along with the pictures. If you have any query, you can ask me at any point. Basically, the rolling technique is used to reduce the residual stresses. First of all, we'll understand this. I'm also running out of time. Okay, anyway, this is the last thing. So that's why I didn't keep that thermal contour, that like whole how to destructive testing. How can we measure? What are the principles like backs the and all. I thought of explaining that also, but because of time constraint, I didn't keep that thing. Okay, I think initially in I think second session I have explained this, but then also for the sake of clarity, I'll explain. So this is a three bar element. These are three same material. These are fixed. Suppose this is at room temperature. All three are at room temperature. So then I'll only heat the middle bar. So I will heat the middle bar. So it will expand. It will try to expand, but these two bars won't allow it to expand. So what happens is some kind of compressive stresses will be generated, and in these things tensile stresses will be there. So once the heating stops and once the heating stops and we allow it to cool down. So then what happens? Since because of thermal expansion of a given of a material and it's a material property, since its temperature is reducing, it tries to contract. It tries to contract. Since it is at more temperature and try to contract, but these two are at these three is a three bar arrangement, right? It's fixed, so it won't allow it to contract. So it won't allow it to contract. Means because of this bar arrangement, it will try to like apply stress. So in this bar, some kind of tensile stress will be generated, and next to this thing, residual stress will be generated. So similarly, what we understand is, if we look into the same analogy, if we compare it to the welding of any butt joint or lap joint or anything, uh, so after once the welding is completed, there will be tensile residual stresses in the welded zone and adjacent zone, and away from that zone, we will be having compressive residual stresses, like this three bar arrangement. So what we understood is there will be the tensile residual stresses. So to reduce this residual stresses, if we apply the compressive stresses, the stresses will get cancelled, right? I think okay. Yeah, tensile stresses will be generated to if we apply the compressive stresses at this particular region, uh, uh, then the residual stresses will be reduced. Sorry. Okay. So residual stresses will be reduced. If we apply some kind of compressive stress, residual stress will be generated. Anyway, compressive stress is not a problem in this away from the component. Uh, Only tensile resistance is the main thing. Means it will affect the fatigue life of the component. So we need to reduce it. So somehow we need to introduce the uh, compressed stress. So what various researchers based on the study and understanding what they tried was like some kind of hammering. Means they'll apply hammering force, or some kind of short pinning. Means they'll take the some metal balls and they'll hit the welded component with the metal balls, so that at the particular localized region, so that compressive stresses will be generated. Compressive stresses will be so if they hit with a balls or some kind of hammer, so compressive stresses will be generated. So with the help of that, we can remove the tensile residual stresses. So that is one of the thought process. So along with that, even researchers developed a rolling technique. What they did was like after joining, they with the help of roller, they will roll above the deposited component like this. So as I explained in this figure, so this will roll like this. It will go. This is the butt joint, and this is joined here. So it will roll here. So once rolling is done, mm, uh, obviously localized compressive stresses will be generated. So because of this compressive stresses, that are already generated tensile stresses because of the welding process, it will be compensated or alleviated, means reduced. Means cancel each other, because compressive stress I am applying because when there is a tensile stresses. So because of that, stresses will be reduced. At least the magnitude will be reduced. Uh, like that, again, the further researchers has carried out to improve the effectiveness of this rolling. They have changed the profile and also these things. Basically, the from figure B to G, this is for a 3D printed component. There also will observe residual tensile stresses in the component to alleviate that. We need to somehow we need to generate the compressive stresses. For that, we can use rolling, short pinning, hammering, some kind of compressive stresses we need to apply localize this. If it is short bolts, they will hit with the short pinning. So compressive stresses will be generated to elevate the tensile resistance generated in the component. I think I made it clear. So in the earlier problem, what it was, so which of the following technique used to minimize the tensile stress in the component? Basically, these are used to reduce the residual stresses. And also, see this appropriate sequence. I said today I don't have the figure. Today I don't have the figure. Uh, Today I don't have the figure. In future class, if time permits, I will show that. In time permits, I will show that to you guys. So surface rolling and short pinning is also used to relieve the residual stresses. I think I made it clear. Let me see if you guys have any doubt. So this was the thing. Yeah, I will see if anyone has chatted in the chat box or something like that. Okay, I think Vivek, you understood, and the rest of the students will understand the rolling thing. If possible, in next class I will explain about this thing also. So I think we can wind up this session. Okay. No any doubts like that. Okay, bye.